Okay, so today I'm going to talk about L'Hopital's. L'Hopital's rule is another tool in the toolkit to deal with limits. There's going to be some problems that we can use methods that we've already learned, and we can also use L'Hopital's. There's also going to be some limits that we were able, or that we weren't able to do, and now we are. So it's a very helpful tool. So here's the deal with L'Hopital's. First of all, we're given two functions, one in the numerator, one in the denominator. They need to be differentiable at least around wherever we're taking the limit. This is something that generally isn't going to be much of an issue, but it is something we have to be conscious of. So the criteria for L'Hopital's is that our limits are in the form of 0 over 0 or infinity over infinity, and those can be plus or minus. By the way, this also works if we have a limit that's going to infinity. So if our c is plus or minus infinity, and as long as we have these criteria that top and bottom are 0, which by the way is commonly what happens with limits, or plus and minus infinity, top and bottom, which we saw when we were doing like horizontal asymptotes and things like that. So, you know, part of this is just going to be getting used to this, seeing from the example, but definitely get this down in your notes, and then we will do a few examples here. Okay, so the first limit we're going to start with is one that we've done already, so let me just remind you the way this works. It's very important in this context that we keep in mind that the way we deal with a limit as we approach a single number like we have here, we have a 0 in the denominator, versus a limit that plus or minus infinity, we compare those differently. So here, let's do this the way we did it at the beginning. So we would rewrite this as the limit as x approaches 1 of x plus 1, x minus 1, that factors. And then essentially what we're doing is we're removing the problem, and we get 2 here. So the problem has been removed, so I can plug in 1, and I get 2, and that's my limit. So what I'll tell you is, what you're going to see with L'Hopital's, that's probably the easiest way to do this problem. The way L'Hopital's work, especially with the, we have to always do these preconditions here, it's going to be a little bit more work. But there are going to be some limits where down the line, that's our only option. So I just wanted to contrast that here. So if I'm going to use L'Hopital's, so the first thing I have to do, and this is a very important step, is I have to make sure I'm confirming that L'Hopital's will actually hold. So what we need is this form of 0 over 0, which we have here, or plus or minus infinity over plus or minus infinity. I do have to write this out explicitly. I can't just say 0 over 0. So I have to write the limit as x approaches 1 of the function on top is equal 0, and the limit as x approaches 1 of the function on the bottom is equal 0. So already we're doing more work than we would do earlier in the year. And now, once we get this to hold, well then I know by L'Hopital's I can take the derivative of the top, which is going to be 2x, and the derivative of the bottom, which is just 1. Notice we're not using quotient rule here. You're taking the derivative of the numerator separate from the derivative of the denominator, no quotient rule. A common error with L'Hopital's is people will do quotient rule. So we plug 1 in and we get 2 and we get the same thing. So unless I explicitly say that you have to use L'Hopital's, which means you're going to do all this, you would have your choice of which one you would want to do. Let's do an example where our only choice is L'Hopital's. Okay, example 2. We still have that form of 0 over 0, but this is not when I can just remove that by factoring it or something like that we saw the last one. So really our only option here is L'Hopital's. So once again, if I plug 0 into the numerator, sine of 0 will give me 0. If I plug 0 into the denominator, I'm also going to get 0. So we first start off, like I showed you before, we write the limit as x approaches 0 of sine of 3x is equal 0, and the limit as x approaches 0 of x is equal 0. So now once we do that, now we can apply L'Hopital's. So the way L'Hopital's works, once again, we're not using quotient rule. We're taking the derivative of the numerator separate from the denominator. Let's start with the denominator. That's really easy. The derivative of x is just 1. The numerator, we got to use chain rule here. So the derivative of sine blob will be cosine blob, and then we have to take the derivative of the blob, which is 3. Okay, so now I can plug in 0 and what I end up getting is cosine of 0, which is 1. 1 times 3 is 3, and that's our answer. So not too bad. You know, it's just a matter of using our derivative skills. Let's do a few more examples, and then that will be it. Okay, let's talk about example 3 here. This is also one I could technically do without L'Hopital's, even though the algebra, a lot of you would struggle with this. I think most of you will find this easier with L'Hopital. So once again, we get this, if I plug 0 into the numerator, I'm going to get e to the 0 power, that is 1. 1 minus 0, or excuse me, 1 minus 1 is going to give me 0 in the numerator. Same thing in the denominator. E to the 0 is 1, 1 minus 1 is 0. So then what I'm going to do is, I'm going to do the preconditions. Always have to do those preconditions. So the limit as x approaches 0 of e to the 2x minus 1 equals 0, and the limit as x approaches 0 of e to the x minus 1 is equal to 0. Once we get that 0 over 0, now we can use L'Hopital. So once again, we're going to take the derivative of the numerator separate from the derivative of the denominator. Derivative of the denominator, that's just e to the x. Derivative of e to the x is e to the x. The minus 1 zeroes out. Derivative of e to the 2x, we got to use chain rule. So the derivative of e to the blob is e to the blob, and then take the derivative of the blob, and there you go. Okay, now you'll notice that we can plug in the 0. E to the 0, e to the 0, both of those are going to be 1, so I'll get 2 over 1, or just 2, okay? Let's look at this problem. As I mentioned, we can use L'Hopital's even if we're talking about a limit where x goes to plus or minus infinity. Now this one's in the form of infinity over infinity. Now in the past, the way we did these limits as x goes to infinity, we've compared sort of strength of function. Once again, I want to remind you, if the stronger function was on top, this limit would go to plus or minus infinity. If the stronger function was on the bottom, this will go to 0. If the function strengths were matching, then we would look at like coefficients, and those constants would end up being our limit. You might realize that e to the x is greater, and then therefore this is 0, but if we want to confirm using L'Hopital's, we want to write out those preconditions. So the limit as x approaches infinity of x, that's equal to infinity, and the limit as x approaches infinity of e to the x, that's also infinity. So I can apply L'Hopital's, the two forms, 0 over 0 or infinity over infinity. And these can be negative infinities. One can be positive, one can be negative. You can still apply it. So let's apply L'Hopital's, the limit as x approaches infinity. Take the derivative of the top, that's 1. Take the derivative of the bottom, that's e to the x. Now it's very clear we have 1 over infinity. If I take 1 and divide it an infinite number of times, that is 0. So L'Hopital's kind of gives us a better look at that stuff. Okay, let's do 2 more examples, and then that will be it. Okay, these last 2 examples I wanted to include because in this context, we start talking about L'Hopital's and people just start applying L'Hopital's. They don't give it a lot of thought. L'Hopital's has to be in that form of 0, 0 or infinity over infinity, so you do have to check this. So for instance, here I want to point out, we do not have 0 over 0. If I plug 4 into the top, I get 0, but be careful, I plug 4 into the bottom, I'm getting 16 plus 2, that's 18. I'm not applying L'Hopital's. 0 over 18 is 0. Okay, so you got to watch out for that. You always got to test that, and as I talked about, those preconditions are very important. Same thing here, realize that I get infinity if I plug that in the top. I actually get 0 if I plug infinity in the bottom. E to the negative x, so if e to the x looks like this, right? E to the negative x would flip the axis, it looks like this, so this is actually going to 0. Now, algebraically, we can see this a little bit better. Since it has a negative exponent, I can move it to the numerator, and I get x squared e to the x. Now, in this case, it's very clear that this is going to be infinity over 1, so that's infinity. So the moral of the story for example 5 and example 6, don't get mindless about this stuff. Think about what you're actually dealing with. L'Hopital's, once again, can only be used in that form of 0 over 0 or infinity over infinity, plus or minus for either one of those. Okay, so that's L'Hopital's rule. This doesn't line up with a particular section. So there you go.